We'll welcome here Florian Delavaud, software engineer at Capgemini, and De Juan, solution architect managing at Capgemini, for a talk on how to optimize an image processing chain with artificial intelligence. Thank you.
Hello? Oui, il faut le coller là. Hello? OK.
C'est ça, ouais. On savait que le prendre en première partie, c'était pas top.
Le blip, il est là?
Pour faire défiler, c'est... Faut l'allumer peut-être.
Non, je pense pas. Essayez.
Pour faire défiler, t'as la zapette. Ah oui, là, il est allumé.
Direct.
On enchaîne là. Ah ouais. Ah non, on enchaîne.
No. So let's go. So thank you everyone to stay here with us. So today I'm going to present you our study with a CNES. Is a R&T to optimize an image processing with artificial intelligence, of course, and machine learning. So the first thing to know is what is an image processing chain. So basically it's unitary processing sequence. We have data from satellite need to be processed. In our study, we have simplified with 3 steps, A, B, C, to be original, and each A, B, or C is composed to 1 to 3 jobs.
So, okay, thank you, Florian. So, the idea here is, why do we need artificial intelligence? Let's say we have a lot of data. What does this mean? A given image from a satellite is made of 10,000 pixels by 10,000 pixels. So there is still a lot of images. If we take the processes of Sentinel-1 and 2, they have to cover all the Earth. Actually, they do cover all the Earth surfaces in 5 days with pictures of 1 kilometer, 100 kilometers per 100 kilometers. So you know they have still a lot of data. Then the algorithms inside, in order to transform the different processes, are very complex. We don't only have 1 or 2 colors, as we can define in images, but we have bands inside the data. For example, Sentinel-2 has 12 bands inside 1 pixel. So the data is really very important. And also we have, as I say, a lot of satellite images. So in this process, we thought that artificial intelligence will be the right solution. And that is exactly what we're going to present here. So, well, as we said, that we are in a process to make jobs sequentially. So the idea is, what does an orchestrator? And what is the process for that? An orchestrator, what it does is that we have a different set of jobs to perform. So the first thing is to take one job and then to send it to a given location of the cluster. So that's one thing. Then the other thing is that once the job is started, he monitorizes that. He has to ensure that he will not consume all the resources that we have pre-described. So the resources are the RAM, the memory, the number of CPUs, and also the maximum time. What we don't want is for one single job that will shut down your cluster, as generally happened on a long time ago with Excel. We just open your Excel in your PC computer and suddenly everything frozen, and then you have to restart your PC. A cluster should never be restarted due to this problem. So that's exactly what does a cluster.
So let's play a game. In our problem, we can imagine the cluster is Tetris, like that. We have two dimensions. The first one is the resources. We have CPU usage, RAM usage, EO usage, a lot of things. And the second dimension is the time. If we put randomly the job in the cluster, it's not optimizing. So a job like the cluster is composed of time and resources. We have designed two jobs. One is a one-time unit and 4 unit resources, and the one in 2 by 2. This is the result of a random positioning in a cluster. As you can see, there are some blank, some all. It's not optimized. And the global wall time is not optimized too. The solution is to have something like that. It's not optimized, but it's better. We have no hole, maybe one here, maybe a future job can fill this space. So the aim of the study was to use machine learning, to learn to the machine, of course, to know how to fill the blank and how to put the job at a great place with some precondition.
Okay, thank you. So we decided to split the problem with the CNES, of course, that this is a joint process with them, in 2 different tasks. The first task was actually to define these what is the right size of a job? Because initially the size of the job are preset by the user. But by running several times and simulate it, we come up with a methodology in order to optimize the size of a single job. This was done by some standard statistical learning models. So that's what we call the passive agents, which was at the end was just a regression analysis. We have some inputs, and then the output was just CPU and RAM. And then once we have the job very well defined, the second step, which is the learning, the artificial intelligence or the reinforced learning algorithm, is where to put the job in the right place. In the right place with a given and prescribed reward. So here, in some way, we do not ski, but we play Tetris.
So Luis introduced 2 agents. How does it work with the image processing chain? So basically, we have an image processing chain who produce log. Log are data. We need data to do something with machine learning. So the first step is collect the log, so run multiple times the image processing chain. And the passive agent, based on statically analysis and data extraction, could say if the block is correctly fit. When you submit something on a cluster, you say, I need these resources. For example, 2 GB RAM and 1 CPU. When your job is executed on the cluster, maybe only 1 GB RAM is consumed. So why ask for two? So the first step is to give a feedback to the image processing chain to be sure the resources you are asked are consumed. The second step is based on the learning database. We have something, we say this job is this dimension. Now we have to orchestrate them. So with simulation and test, we have an agent active or an intelligent active who could give feedback to the image processing chain to say the perfect order is not A, B, C, but maybe B, C, A. We don't know. And we have a lot of chain launch in parallel, and maybe the solution could be AA, BB, CC. It's better than ABC and NABC. So here you have two representations of a cluster, a 2D one and at the bottom the 3D one. As you can see, there are space, and the aim of this RNT is to optimize this space. Our study is based, as I said before, on CPU and RAM analysis to minimize the global wall time. At the bottom right, you have an extract of a log. All our analysis is based on data, based on this log. So we have processed some data analysis, like this one, the statistical study of the CPU, the RAM, and the wall time. And that's it. So now we have to do some machine learning. We have tested two things. The first one was the genetic algorithm. A genetic algorithm is based on natural evolution. You generate some individu, you keep the best one, you cross the best between them, and we redo that. At each generation, maybe you are better or not, but you will keep always the best. And after generation and generation, you can obtain some interesting results, and it's very quick to simulate. So first step, you define your neural network, you generate randomly your genome, then you evaluate the performance of each one. So it's here very simple, you have to measure the blank or the black, and you keep the best one, you cross them, and like in natural situation, you add some mutation to keep the optimum. And we do, and the result is sufficient for your issue. You have one.
Okay, thank you, Laurent. So after the genetic algorithm, we decided to go to another type of algorithm, which is reinforced learning. How does this reinforced learning works? And the first thing is to really define it, because for reinforced learning, compared to other kind of artificial intelligence, is the most closely to what a human does. Why is that? Because generally what it does is that we try to optimize a reward by dynamically acting through a system, through the environment, through actions. Initially, the agent, so here myself or the bot, he doesn't know the action he has to use, nor the environment. So it's a system, a dynamical system with unknown equations, with completely unknown. So he has to act directly to it. And that is quite new compared to any kind of optimization problem that we have done on dynamical system. So this is the idea. So how does it, I'm going just to have a sketch very quickly. How does it put it in action? Suppose that our system is here, and then I have to go, I don't know, there, in two or three steps. And the reward is the number of steps. If I do one step and I close my eyes and open and say, okay, I think everything is okay, so I can continue. I can continue here, and then I continue here, and then I continue here, and then boom. And no, that was not a good step. So I draw back. Then I do another test. And just by doing a lot of simulation, the agent will learn it. So there is a trade-off between discovering the environment, which may be a good solution, and take useful solutions that we have. That is exactly what does reinforced learning. So the question here is, okay, before that, yes, reinforced learning has been applied in different problems. The first one that everyone really knows is in 2014, AlphaGo, which was a bot who plays the Go player. He won a contest just by using this algorithm. Maybe also in 1992, IBM used it to create a backgammon player. And also the NASA used it in order to optimize the scheduling, the repair scheduling between two shuttle launches. So it's something that has been used. So then the question that we can ask, okay, that's good, but where does the machine learning, the neural network fits in this model? The idea is that if we have to prescribe or describe all the possibilities between environment and states, the possibilities are huge. And up to now, we don't have enough computer power. We have a lot, but we don't have enough computer power. So we have actually to model that. And the modeling of the actions and the modeling of the environment, we model that through deep learning methodologies. Why deep learning methodologies? Well, because neural networks, convolutional networks, they do work very well on images. And then here we are really describing images. And then at the end, we have exactly the same process of optimization that we can use elsewhere in machine learning.
Yeah, thank you, Luis. We can show a demo.
Yes.
Yeah.
So here, on the left-hand side, we have a demo, which is something that has not been learned. We have drawn boxes, and well, is not optimized. However, on the right-hand side, we have exactly the same boxes, and then we have applied this methodology in order to place optimally the boxes. And then we see clearly that...
and what is the difference between us?
Sorry?
The second one was trained.
Yes,
yeah.
The right-hand side was trained, and the left-hand side was just a randomly position of the boxes.
Yeah. So to conclude, we have two approaches. The genetic one, with quickly implemented, quickly ready for production environment, but is not generalizable. If you have to optimize a batch job, is a great solution. But when you have a new batch job, you have to redo the learning process.
On the other hand, the reinforced learning, it's a simulation approach. So we can simulate off-batch all the draws that we want in order to learn the model very closely. So that's one thing. And the other thing is that by using these neural networks, it can be generalized much better than other methodologies. And it can be used for real-time batch processing.
So, and what next after that?
Okay, what next is, well, today we have applied that on a cluster, and we would like to apply that on the cloud. The big difference between cluster and cloud is the scalability, meaning that if you need resources, you just take them. So then the time is not really the real parameters. However, to access the resources is expensive. So the idea will be to use exactly the same methodology in order to to optimize a function between time and resources. But it will be exactly the same.
So thank you for your attention. If you have any questions.
Yes, do you have any questions? Well, thank you very much, guys. Thank you. Let's welcome now... Oops, yes?
What kind of performance improvement have you achieved with such an improvement in machine learning for, the management of jobs on this cluster?
Okay. For real performance, we are about 20% less of time.
For the genetic one. Yeah, we have tried to improve our performance, and we have, it's random, so maybe it's 20, maybe 50. it's less, but we have about 20% of optimization of a global work time on a bad job to refit the job and organize it.
Questions? All right, thank you.